Bismillahirrahmanirrahim. Assalamu alaikum, dear students. I'm Arif and I welcome you all to lecture number 12 on the subject of computer organization and assembly language programming. The title of today's session is Design of Memory Chips. Well, today we will start with a short class quiz. Then I will give a brief and a quick comparison of different types of memories, their access times and capacities. We'll talk about multi-byte uh, read and write operations in the memories using the little endian and the big endian techniques. And after putting the stage right, we will discuss in detail as to how we can design RAM chips of different sizes, write their HDLs, and verify the behavior of these RAM chips on the hardware simulator. So let's start playing. Dear students, in the last session, we designed a single bit register using a 2 by 1 mux and a D flip-flop. For your ease, I have given the block diagram and the detailed diagram of the 1-bit register on this slide as well. The timing diagram over here shows you the load and the inputs to this register during different time intervals. I want you to determine the value of out and draw the signal values uh, using a copy and a pencil. Please stop the video, do that, and then join me. Meanwhile, I move ahead. Before we start with the design of memory chips for our hack computer, let us have a quick overview of the memory hierarchy. Well, this slide shows the bigger picture of our computer system, which we intend designing in this part of the course. We have already designed the ALU and some registers, and today we intend designing the memory. Dear students, when we say memory in computer hardware, we mean many different things, but most of the time we mean the main memory, which consists of the memory that resides actually inside the computer and hardwired into the computer's motherboard. This is also called the RAM or the random access memory, and in most of the cases it is used to store both the data as well as the program. And this is von Neumann architecture, and I will talk about it in detail in the upcoming sessions. Right now, just remember that this control unit over here inside the CPU is responsible to fetch an instruction from the memory, will decode it, and then may fetch the data or the operand on which the instruction needs to operate. After getting the data, the control unit will instruct the ALU to perform the required operation. And finally, the result may be sent on to some output device and may be written back in the memory as well. Well, this is a bigger picture, and we will talk about this in detail when we will design the hack CPU in totality. And for the time being, let's restrict ourselves on the discussion of memory. Well, dear students, accessing a memory location is expensive, as we need to supply an address and then read or write the contents of that location of memory. Moreover, moving the memory contents into the CPU and vice versa also takes time. So the solution is memory hierarchy. So instead of having a single main memory over here, we have a small piece of memory called registers inside the CPU. We have the cache memory, and beyond the main memory, we have the disk as well. Whenever we read some data from the main memory, we keep it in the cache memory as well as in the registers. And while writing back to the main memory, we always write back to the registers, the cache memory, and then the main memory. Since these registers are small memory locations, and this cache is also a bit small as compared to the memory, so we cannot keep the entire data which is there in the main memory inside the cache of the registers. So what data we want to keep inside the registers or the cache memory from the main memory, this depends on two principles, uh, the principle of temporal locality and the principle of spatial locality. And these two principles are mostly taught when discussing the different architectures of cache memory. But for the time being, just remember, as we move away from the CPU, the memory becomes slower, cheaper, and larger. Well, this slide shows the four different types of memory units: the registers, cache, and the main memory, as well as the secondary storage, along with their standard sizes in which they are normally available and the typical speed. Note that it just takes around 1 nanosecond to read a register, while it takes over 100 nanoseconds to read the main memory. From this, you can understand the importance of keeping more frequently used data instruction or more recently accessed data instruction inside the registers and cache. And this slide shows the decimal and the binary terms that are normally used for representing different sizes of memory. Remember, this kilobyte, capital KB, is basically 10 raised to the power 3 bytes, 1000 bytes, while in binary, this KB byte is abbreviated as KIB, which contains 2 raised to the power 10 bytes, that is 1024 bytes, which is of course 2% larger than this. However, in computer science, mostly people represent this 2 raised to the power 10 as KB, which is a bit wrong. You should always use KIB instead. Anyway, please go through this table and have a clear understanding of all these terms and try using them instead. Try using these instead. Oh, well, the computer's main memory is also called the random access memory because irrespective of the size, every word gets selected instantaneously at more or less the same time. It is also known as the read-write memory as it allows CPU to read as well as write data and instructions into it. Well, this RAM is a microchip implemented using semiconductors, and there are two different or main categories of RAM: the dynamic RAM and the static RAM. The dynamic RAM is composed of a capacitor and a transistor, while inside the static RAM there are no capacitors, there are only transistors. Refreshing is required as far as the DRAM is concerned, since there are no capacitors inside the SRAM, so no refreshing is allowed. Uh, the DRAM is comparatively slower and less expensive, while the static RAM is faster and of course expensive. And it is the SRAM which is often used inside the cache memory due to its high speed. Before I proceed, let me touch upon a concept of multi-byte load and store. Dear students, all 32-bit machines load and store 32 bits of data with each operation. Now the question is, how are the bytes of a multi-byte variable ordered inside the memory? Let me describe it with the help of an example. Suppose we have a 32-bit variable having the value of 0, 1, 2, 3, 4, 5, 6, 7 in hex, and this 32-bit value needs to be stored at suppose address 100 in hex. Now the question is, at address 100 only one byte can be stored. Now if we store the least significant byte, that is this 6, 7 at 100, this is the little endian technique. And if we store this byte, the most significant byte at the address 100, this is called big endian technique. So you see inside the big endian at address 100, we have stored the data value, the most significant byte of the data value, 0, 1. and then 2, 3, and then 4, 5, and then 6, 7. This big Indian technique is used by the MIPS architecture as well as the entire data on the entire internet also use the big Indian technique. In case of Little Indian, you store the least significant byte, that is this 67 is stored at this address 100. This 67 is stored at this address 100, and then the next byte, that is 4, 5 at 101, 2, 3 at 102, and the most significant byte at this address 103. The Little Endian techniques are used by the x86 and the ARM processor. Now that we have a fair idea about the main memory, let's now do a bit of scuba diving as to how a RAM chip can be designed. And only after that we will be able to write the HDL code for the RAM chips. Well, dear students, RAM is actually an array of n W-bit registers equipped with direct access circuitry. The number of registers and the width of each register are called the memory size and width respectively. In simple words, you can think of RAM as a sequence of n addressable registers with addresses starting from 0 to n minus 1. At any given time, only one register in the RAM is selected, and it is this register whose value is available on out during any read operation. Similarly, it is this register whose contents will be overwritten during a write operation. To select a register, we need the address of that register, and address width varies with the number of registers or words available in the RAM. For example, here we have a RAM 8 chip comprising of 8 registers, each register of 16-bit. This is the in which is coming into all the registers, and this is the address using which we will be able to write any register by setting the load input to high, and this is the address using which we read the content of any of these registers. So if we have 8 registers over here, 0 to 7, the address bits will be 3. And if we have 1024 registers over here, the addressing bits will be 10. And remember, in this block diagram, this portion shows you that this is a clocked chip, clocked device. So to go into more details of the read-write logic of RAM, just remember that any given point of time, only one register in the RAM is selected, and all the other registers are irrelevant. So the read operation is described over here. To read the contents of register number I, we need to set these address bits to I, and the result will be the RAM output pin out will emit the state of the register I, and this is a combinational operation independent of the clock. So if I place a 5 over here, the contents of register number 5 will be placed on these 16 bits of out. Well, dear students, to write a new data value D into any of these registers, let's suppose I, once again we need to place the address I at these address bits. On the 16 bits of this in, we need to place the data value. While writing, we also need to set this load bit to high, and the result will be the state of that specific register I becomes D, and from next clock cycle onwards, out emits D. This table shows the different chips that we will be requiring to build our hack computer. First of all, the RAM 8 having 8 registers or 8 words, so that's why the addressing bits are 3. RAM 64, RAM 512, RAM 4K, and RAM 16K. Remember, in case of RAM 16K, we have 16384 different locations or registers, each of 16-bit, and of course the addressing bits will be 14. Okay, so let's design the RAM 8 chip. Well, dear students, The RAM 8 chip will have memory of 8 registers. So here we will be having 8 registers. Each register will be of 16 bits. The out over here holds the value stored at the memory location specified by this address. And in case if load is 1, then the 16-bit at this in value is loaded inside the memory location specified by the address. And this loaded value will be emitted out from the next time step onward. Well, this in 16 bits of this in value will be fed inside all these registers. All these registers. This in 16 bits of this in will be placed inside this register, this, and all these registers. Now, in case of a write operation, what we need to do is we need to write into any one of these 8 registers. So we use a DMUX 8-way chip to select one of these 8 registers specified by this address, something like this. So we have the load bit coming over here, load bit, and the address bits are the selection lines of this DMUX 8-way chip. Based on these 3 address bits, any one of these 8 outputs will be made high. So this A is going over here, this B is going over here, and this H is going over here. So depending on this address, any one of these registers will be uh, the selected registers, and whatever is there at the in input will be placed inside that register. So this is how the writing will be done. In case of reading, we use a MUX 8-way 16 chip, which of course we already have designed in the combinational part of this course. And this is used to select the 16-bit contents of the register specified by, of course, the address bits. So the address will be placed over here. This is MUX 8-way 16. So if we have our address 000 over here, the contents of this register, 16-bit contents of this register will be placed on over here, and of course will be placed out. And in case if we have the selection address 111 over here, the 16-bit contents of this register will be here and will be placed on out. So this is how we will be able to read this RAM 8 chip. Okay, now I think we are well equipped to write the HDL for this RAM 8 chip, that is memory having 8 registers, each of size 16 bits. It's quite simple. In the last session, we have already written the 16-bit register chip, which is whose HDL is shown over here. And the interface part of this chip tells us that it has 2 inputs, a 16-bit data word and a single bit load bit, and it has a 16-bit output. The implementation part tells us that we have used 16-bit chips to implement this 16-bit register chip. If you're not clear about this, I strongly recommend that you should go and check out how we have designed this register chip. So over here, if you see the interface of this RAM 8 chip, you see that it has a 16-bit input, a single bit load input, and a 3-bit address input. Why 3? Because we have 8 registers. And the same can be seen over here in the block diagram as well. Moreover, in the HDL part, you can see a 16-bit output as well, which is shown over here. Well, since this RAM 8 chip is having 8 words or 8 registers, so in the implementation part, you can see that we have simply used 8 register chips, 8 register chips. And note that the 16-bit in is common to all the registers. The 16-bit in is common to all the registers. However, the load and the out bit are a bit confusing. To understand this, let me fall back to the previous slide. Over here, you see this 16-bit in is common to all these registers, while this single bit load input is supplied to any one of these registers any one of these 8 registers depending on this 3-bit address or the selection bit of this 1 by 8 mux, 1 by 8 demux. Let me move on to the HDL code. And over here you see the demux 8-way chip in which the first input is load, which is supplied to any one of these 8 outputs A, B, C, D, E, F, G, H, depending on this address. Let me move on to the previous slide again. This load input was for writing any one of these 8 registers in this RAM 8 chip. Now, as far as the reading is concerned, reading any one of these 8 registers is using the same 3-bit address, which is supplied over here in the selection lines of this MUX 8-way 16 chip. So, whatever address is supplied over here, the 16-bit data of the specific register is placed on the out of this RAM chip. Let me move on to the HDL again. And at the end over here, you see the MUX 8-way 16 chip. And depending on this address, any one of these 8 inputs, A, B, C, D, E, F, G, H, is placed on, uh, on the output of this RAM 8. Dear students, I have tried my best to make you understand the design of RAM 8 chip. If you still have confusion, please go through this part of the video again to have a clear understanding. And now it is time to move on the hardware simulator and verify the working of a RAM 8 chip practically. So let me move on to the terminal. The hardware simulator is already running. Let me load the HDL file for RAM 8 chip by clicking this load chip button. And inside the session 12, we have different chips, and this is the RAM 8 chip. Let me load this chip. In this HDL pane, you can see the HDL code that we have discussed in detail. In the input pane, you can see that if we want to write some data, we will place it in the 16-bit in value. And let me place, let's suppose 1, 2, 3 over here. I want to write 1, 2, 3. And since I want to perform a memory write operation, so I need to make the load too high. Let me make it 1. And I also need to give an address where I want to write this data. So I know this is a RAM 8 chip, so we have a 3-bit address. I can give addresses from 0 to 7. Let me give 4. So I want to write data value 1, 2, 3 at address 4 inside this RAM 8 chip. I have made the load as well high. And now let me do a tick and a talk. A tick and a talk. So you see the value is written over there at address 4. Let me also write a different value at address 2. Let me make the address 2 and let me uh, give the value, let's suppose 697, and let me do a tick and a talk. So 697 is also written over there. Let's try reading the address 4 now. I want to read the address 4. And since I want to read the address 4, I need to make the load to 0. And the in value does not have any effect during a read operation, so we don't change it. And let me do a tick and a talk. You have noted that uh, when I have done the tick, the read operation has placed the value 1, 2, 3 at this place out. So this will make another point clear to you all that writing is more expensive operation as compared to reading a RAM chip. Well, dear students, do play around to have a clear understanding of the working of this RAM 8 chip. And let me load the built-in RAM 8 chip and see its behavior. Let me load the built-in RAM 8 chip by going inside the tools directory. which you all have downloaded. Inside tools, let me go to the built-in chips, and inside built-in chips we have the RAM 8. Wow. So you see the built-in RAM 8 chip, which is implemented as a Java class inside this hardware simulator, as you can see inside this HDL pane. It also have a additional GUI effect as well. So you can see the RAM 8, the 8 different addresses and the values. 8 words inside this RAM from address 0 to 7, and all initialized to the value of 0. Let me load a value of, let's suppose, 278. Let me make the load bit too high, and let me write it at address 1, and let me do a tick and a talk. You see, on a tick it is there, and on a talk we have got it over here. So there is another easier way to use this GUI and write values over here. Let me write uh, direct values by clicking this -27, and let me write over here minus 876. So these are the values inside this RAM. If you want to read it now, just make the load 0 and give the address over here. Let's suppose I want to read the address 7. So I place a 7 over here. I do a tick and you see the value is there. The reading is quick fast. Okay, let me read the value. Let's suppose uh, 2, and we know the value at 2 is 143, so I do a tick, so this 143 is there. Okay, so that's great. Moreover, this GUI effect also provides you the provision of searching the RAM. You give the address. Let's suppose I give the address of 4 and I search it, and you see this 349 is there over there. And of course, if you change the format to binary, you have the binary effect over here, but over here you still have the decimal values. That is great. Let's fall back to the slides. Well, dear students, the hard part is over. Uh, you can now use bigger RAM chips easily using this RAM 8 chip. Remember, this RAM 8 chip has just 8 registers. You can use this RAM 8 chip to build or design a RAM 64 chip, which will of course contain 8 RAM 8 chips. And similarly, you can use this RAM 64 chip to build or design a RAM 512 chip having 512 16-bit locations, and this RAM 512 chip will be composed of course, RAM 64 chips, and the same technique can be used to implement RAM 4K and RAM 16K. So this slide shows the HDL for RAM 64, and in the chip interface, just note the address. We have address of 6 bits, and the least significant 3-bit of this address, these significant 3 bits 0, 1, 2 are used by the RAM 8 chip, while the most significant bit, that is 3, 4, 5, are used by the demugs 8-way as well as by the mugs 8-way 16. And I hope this makes sense to you all now. Well, in the same pattern, this is the HDL for the RAM 512 chip that uses 8 RAM 64 chips. And similarly, this is the HDL for RAM 4K chip that uses 8 RAM 512 chips. And finally, this is the HDL for RAM 16K chip that uses naturally 4 RAM 4K chips. So that is it, dear students. That is all for today's session. Uh, we have designed the RAM chip for our hack computer today. Do practice running all these chips in the hardware simulator. Do write the code of the bigger chips as well. And the interested students should also try to implement RAM chips having a word size of other than 16 bits and try running them on the simulator as well. I hope today's session was informative for you all. If you have liked it, please subscribe my YouTube channel and share it with your friends. I wish you all the best, happy learning, and Allah Hafiz.